Welcome to our class notes on 8-10, single displacement or single replacement reactions. These are very important notes. Please watch the notes carefully. You'll need to understand these notes fully to be able to do our homework assignments and be able to answer our essay question on the next test. Our essay question will require you to draw what happens during a single displacement reaction. So with that said, let's talk about how to draw what is going on in single displacement or single replacement reactions. In this particular first reaction that we're going to be looking at, it involves active metals replacing less active metals. We did a lab where we looked at which metals were more active than others. We created an activity series during that lab. Activity series reveals which metals are more active than other metals. If you drop an active metal in a solution, an aqueous solution containing a less active metal, the more active metal will replace the less active metal in solution, causing the less active metal to precipitate out. Here's an example. Example number 1. In this reaction, they are dropping sodium in a solution containing aluminum nitrate. Aqueous solution means that salt aluminum nitrate has been pulled apart. How do I know aluminum nitrate is a salt? We have a metal with nonmetals, in this case a polyatomic ion, the nitrate ion, which is minus or 1 minus. And when you drop that in water, water will pull it apart. So the aluminum ions will be floating around and the nitrate ions will be floating around. Can sodium replace aluminum? In order to tell, what we need to do is look at our activity series. Here we have sodium. It's at the very top of the chart. It is in the extremely active metals range of the chart. Beneath it, in the also active but not quite as active section of the chart, we have aluminum. So sodium is above aluminum. Sodium can replace aluminum ions in the solution. So here we go. Sodium replacing aluminum. Aluminum is 3+. How do I know that? It is in family Roman 3, group 13. It has 3 valence electrons. It is 3+. If you uncross the charges here, this 3 came from the aluminum, which is 3+. Aluminum doesn't have a subscript here, which is understood to be 1. The nitrate ion is 1-. So when they wrote the formula, the 1- from the nitrate ion was brought down to the aluminum. The 3+ from the aluminum was brought down to the nitrate so that the charges would balance. So these aluminums will replace the nitrate. The formula for sodium nitrate, which is the salt that is formed, is NaNO3. Why is that? Because sodium's in family Roman 1, group 1. Its charge is 1+. So they bring a 1 down to the nitrate ion. The nitrate ion's 1- went to the sodium ion. The charges were crisscrossed. The formula is NaNO3. In order to balance the reaction, I have 3 nitrate ions. So I'm going to need a 3 in front so that the nitrate ions, law of conservation of matter mass is followed. If I put a 3 in front there, I need a 3 here. I have 1 aluminum on the left side. I only need 1 aluminum on the right side to balance. So here we go. Let's illustrate what really happened here. The 3 sodiums were dropped into the solution. Again, sodium has 1 valence electron, so it only has 1 dot. In the solution, remember, aqueous means it's been pulled apart. So I have 3 nitrate ions floating around with the subscript 3, and I only have 1 aluminum ion at 3+ floating around. Again, aluminum's in family Roman 3. So this first thing, we're dropping the 3 sodiums in. That's what's happening before the reaction. This next container is what is happening during the reaction. There's our 3 sodiums. The aluminum's 3+. Each sodium, since it's more active, will force their electrons onto the less active aluminum. It'll take 3 electrons. Why? Aluminum's 3+. The nitrate ions, the minus, they really didn't do anything here. They're still floating around. So here's what this reaction, this beaker's what was happening during the reaction. This beaker's not what is happening after the reaction. Each of those sodiums gave up their 1 electron, so they become 1+. The aluminum has taken all three. It has lost its 3 plus charge, so there's no longer anything that is able to hold the aluminum in solution, because remember, in order to be an aqueous solution, in order for metals and nonmetals to be held in water, they have to be charged. Water is polar covalent. It can grab onto the ions and hold them there. Polar covalent means water is partially charged. The partial charges of water will enable it to hold in the full charged ions. Aluminum is no longer charged. It precipitates out of solution. Here's our chemical equation. What we're really showing in these beakers is what happens when the sodium's dropped in. Aqueous here means that water is pulling apart the aluminum nitrate. So the Al3 plus is pulled apart by water from the 3 nitrate ions. An ionic equation is really showing what happens to the ions in this reaction. What happened here is these 3 sodiums gave their electrons up and became 3 plus. The 3 nitrate ions stayed floating around in the solution. And the aluminum 3 plus took 1 electron from each of the sodiums and became neutral again. So on the right side, it formed a solid which precipitates out. Instead of writing solid here, you can put an arrow going down, which means it precipitates out of solution. A downward arrow means the same thing as a solid. So the ionic equation is showing what really happened in here. On the left side of the equation, we have the 3 sodium ions. There they are. There's the aluminum 3 plus right there. Here's the 3 nitrate ions right here. On the right side of the arrow, they're showing what happened here. We now have 3 Na pluses. There they are. I still have the 3 nitrate ions. There they are. And aluminum is no longer charged and it precipitated out of solution. There it is. So the ionic equation is really showing what happened in the middle beaker during the reaction, and the bottom beaker here, what happened after the reaction. A net ionic equation is really just going to show us what the overall change was. As we showed you, the 3 nitrate ions are in all 3 beakers and nothing happened to them. When nothing happens to them, it is called a spectator ion. So the ion that does nothing is the spectator. It just stood around and watched. The net ionic equation gets rid of the spectator ion. It gets rid of the thing that did not change. On the left side, I have 3 nitrates. On the right side, I have 3 nitrate ions. Nothing happened to those. So you could cross those out, and that would give you the net ionic equation. It got rid of the spectator. Why is the sodium still in there? Because we started with 3 NAs and we finished with 3 Na pluses. Why is aluminum in there? We started with Al3 plus and we finished with Al. Those 2 things underwent the change. Another example is shown right here. This is example 2, also showing an active metal replacing a less active metal. They want us to show what happens between calcium metal and aqueous iron 2 chloride. Metals replace metals. So first of all, let's determine if a reaction happens. Is calcium more active than metal? To find that out, we look at our activity series. Here's calcium at the top of the chart in the group of the most active metals. Here's iron, much further down. Calcium is way more active than iron. So, yes, calcium will displace iron. So let's write the chemical equation. Here's calcium. We're supposed to look at iron 2 chloride. Iron 2 chloride is when iron is 2 plus. Chloride is a halogen. It is an element that is in family Roman 7, so it becomes 1 minus. So we have the 1 minus chloride, we have the 2 plus iron, crisscross the charges, we have FeCl2. What happens in this reaction is calcium is going to replace the iron. So calcium will join with the chloride. Calcium is in family Roman 2, group 2. It has 2 valence electrons. It will become 2 plus. I have 2 plus calcium. I have the 1 minus chlorides, crisscross the charges. We end up with CaCl2, and we have iron displaced. So in our first beaker, we're going to show what happens. Calcium's in family Roman 2. It has 2 valence electrons. Aqueous means that it will pull apart. Water will pull apart the FeCl2. So the Fe2 plus is pulled apart from the 2 chloride ions. We do not write Cl-2 because the water pulls them apart. So here's the 2 Cl minuses. There's the Fe2 plus, and we're dropping in calcium. So on the left side of the reaction, this is what we're seeing really in these first 2 beakers. On the right side of the equation, we want to see what happens afterwards. During the reaction, the more active calcium metal is going to force those 2 electrons onto the less active iron. Iron will take 2 electrons because it's 2 plus. So in the right side, we now see iron has calcium's electrons. When it gained those 2 electrons, it will go from 2 plus back to neutral. It will precipitate out of solution. That would be an arrow pointing down. Calcium got rid of its 2 electrons, as we see here in the middle beaker, causing it to become 2 plus. There it is, calcium 2 plus. The chloride ions are still floating around. They didn't do anything. So our ionic equation, Ca plus F2 plus 2Cl minus will go to Fe, which is shown here, Ca2 plus, which is shown here, and the 2 chloride ions, which are floating around. Who's the substance, or what is the substance that didn't change at all during the reaction? It was the 2 chloride ions, but you can just write Cl minus. In our net equation, we get rid of the spectator ion. We get rid of the one that didn't change. Calcium went from solid metal, which we dropped in, to become aqueous Ca2 plus, which we see here on the right. It changed. It's not the spectator. Fe started out as 2 plus and it went to neutral and precipitated out of the solution. It changed. The 2 Cl minuses did not change. They're the chloride ion, so we would cross out those. The one that did not change, you can cross out, and that will give you the net ionic equation. So in our first video here, we took a look at what happens when active metals replace less active metals. In our next video, we're going to take a look at what happens when active metals replace the hydrogen ions in solution.